Hello everyone. Now in this video, let's look at the magnetic field of a solenoid. Now we have a solenoid 0.5 meters long, has 200 tons. Now the magnetic induction near the center of the solenoid is 0.08 Tesla. Now what is the current in the solenoid? That is the flow of currents, okay, the current that flow or pass through the what? Solenoid. Now solenoid, okay, a cylindrical coil of wire acting as a magnet when carrying electric current. That means when current is passed, or when current is passed through a solenoid, then it behave or act as a magnet. So that's why I said it is a cylindrical coil of wire acting as a magnet when carrying current. Now, to be able to understand to be able to determine the direction of magnetic field in a solenoid. Now there's this simple rule that is usually applied, in order to what? To understand, to determine the direction of magnetic field, okay, in a solenoid. Now let's look at how to, using diagrams, okay. Let's learn about how to determine the direction. Okay, let's learn about how to determine the direction of the magnetic field, the magnetic field, okay, in a solenoid. Now, let's say we have the magnetic lines of induction, also known as magnetic field lines of force, entering the solenoid on this end, okay. Then the lines are leaving the solenoid, okay, at this other end. The lines are leaving the solenoid at this other end. Okay, now let's say we have, this is the what? The wire, okay, that is the wire wounded, okay, wounded around the wall, the coil, okay. So now the current entering the coil is I. So we have the wire, okay, the wire wounded around the what? Around the coil. So this is what solenoid looks like, okay. Now, according to the rule, okay, according to the rule, okay, it was established that when the coil is viewed from one end and the flow of currents, okay, at that end, okay, is in the what? Anti-clockwise direction, then that means that that end will be what? North pole, okay. Then it will be south pole when the flow of current is in the clockwise direction. So in this case, now we have the current entering the what? The coil, okay, from this end. Okay, let's talk about that. Now let's say we now have the lines of, that's the lines of magnetic field, okay. We have the lines of magnetic field, then the currents, okay. Now this is the current entering the coil. So we have the wires, wrapped or wounded around the coil like this, okay. And then, so because now this end will be the south, okay, that is because when viewed from this end, when the coil is viewed from this end and the flow of current is in the clockwise direction, then this end will be the what? The south pole, okay. Now, so which means that the lines of magnetic induction are entering the coil, okay, through this end, and they are leaving the coil on this other end, okay. These are the lines of magnetic induction leaving the what? Leaving the coil. So this is the north, so which means this other end, okay, this other end, let me draw this other end, okay. So the what? The field lines, okay, will be moving in this direction. Why here? The field lines will be moving in this direction, and this direction is what? This is clockwise direction. We have clockwise direction. But when we have the direction, okay, this other way, okay, then we have what? Anti-clockwise direction. So this is anti-clockwise. We have this to be anti-clockwise direction. Okay, so So this is what it looks like, you know, when it comes to how to determine the direction of magnetic field in a solenoid. Like I said, when viewed according to the rule, okay, when the coil, okay, when the coil, that is the solenoid, when the coil is viewed, when it is viewed from one end, and the currents at that end, okay, flows in the anti-clockwise direction, okay, then that end is the north pole. That end is the what? Is the north pole. That'll be the north. Okay. Now conversely, if the current flows in the clockwise direction, if the current flows in the clockwise direction, okay, if the current flows in the clockwise direction, then that end is the south pole. That end is the south pole. So now, so the magnetic field, that is to calculate the magnetic field of a solenoid, we have the formula B equals to permeability of free space multiplied by number of turns per length, okay, then multiply by the current entering the solenoid. Remember, we want to find the value of I, which is the current in the solenoid. So to be able to calculate the value of I, so we can express I in terms of the magnetic field strength or the magnetic induction, okay, and every other quantities or parameters. So we have this to be magnetic field intensity or the magnetic flux density, also known as the magnetic induction, okay, over the permeability of free space, number of turns per length. Okay, now let's find out. So first, we know that the value of B is 0.08 Tesla. Okay, now then the value of permeability of free space is 4 pi times 10 raised to the power of -7, okay, Henry per meters. Okay, Henry per meters. Now number of turns, this is number of turns per length. So we have the number of turns to be 200 and the length of the coil is 0.5. So which means in this case N will be 200 divided by 0.5. Okay, so 0.5 is 1/2, so that will be 400. So the number of turns per length will be, this will be 400 per meters. 400 per meter. So we have the current to be equals to 0.08 Tesla, okay, over the value of permeability of free space, which is 4 pi times 10 raised to the power of -7, okay, Henry per meters. Then so multiply by 400, okay, multiply by 400. So in this case, at the end of the day, you know, when we combine the units, we have Henry per meters, okay, multiply by, that's Henry per meters multiply by per meters, which is the unit of number of turns per meters. Okay, so we are going to have 0.8. Let's get the value of what is 4 pi, okay, 4 pi multiplied by 400, that'll be 5027. Okay, so we have 0.08 Tesla over 5027.2 multiplied by 10 raised to the power of -7. Okay, so we know that the unit here will be what? Will be the amperes. All right, so let's move the decimal points. 1, 2, 3. Okay, so this will be I equals to 0.08 over 5.02 0.72, okay, times 10 raised to the power of 3, then multiply by 10 raised to the power of -7 amperes. So current I would be, so let's divide, now let's divide what is 0.08 divided by 5.027, okay, 5.0272, okay, that will be, so we have that to be 0.01591, okay, multiply by, now we have 3 minus 7, that will be -4. So then, you know, because we have 1 over 10 raised to the power of -4, so that will be 10 raised to the power of what? 10 raised to the power of 4. So this will be 10 raised to the power of 4. So when this is multiplied by 10,000, which is 10 raised to the power of 4, okay, that will be 159. So the current is 159.1, okay, amperes. The current is 159.1 amperes, and that is the current in the what? In the solenoid. Remember, solenoid is a cylindrical coil of wire, okay, which behave or act as a magnet when it is carrying current or when current is passed through it, okay. And like I said, you know, when the coil is viewed from one end and the current at that end flows in the what? In the anti-clockwise direction, then that end is the what? Is the north pole, okay. So which means for anti-clockwise direction, in this case, this will be the north because the current flows in this direction. Now this will be the what? Clockwise direction, okay. This is clockwise direction. Why this is what? Anti-clockwise direction. So this is clockwise, okay. This is clockwise direction. And why this is what? Anti-clockwise direction. So then if the current flows in the clockwise direction, then that end is the what? Is the south pole. The noblest pleasure is the joy of understanding. Bye bye.